Hey, everybody. Thank you for coming to another EERI seminar. Today we have Dr. Saj Salam. He is a senior engineer in the civil engineering and structural engineering practice at Exponent in the Oakland office. He specializes in computational geomechanics, numerical and analytical analysis of geosystems, and condition assessment of geotechnical assets. He also is an expert at natural man-made slopes, embankments, retaining structures, roads and highways, ground improvement, earth dams, and I'm sure many others. Dr. Salam is also adept at both like reactive and at proactive consultation alongside risk assessment. And otherwise, he uses his multidisciplinary background in engineering statistics to help deliver solutions to the people that need them. So with all that being said, take it away.
Hear me? Yeah. Thank you very much for the introduction. Just here I see that there are two people entered the waiting room. So
we'll take care of it.
Okay. Yeah, thanks for the introduction. I want to thank the department for inviting me to be here today to present about the forensic engineering and failure investigations that we do at Exponent. So I'm going to start with a brief introduction about myself beyond what Noah was saying. Let's see. Yeah. So my name is Saj Salam. I'm a senior engineer with the civil and structural engineering practice at Exponent. I got my bachelor from Sharif University of Technology back in 2014, and then I came to the States to start my graduate studies. Then I got my master from Southern Illinois University in 2017. I was working mainly with Illinois Department of Transportation, and the outcome of my work was proposing some quality aggregate selection charts based on their index properties like fines content, dust ratio, and plasticity index. Then I worked in industry for 1 year and then started my PhD at Pennsylvania State University and graduated in 2020 with a minor in statistics. And there, my work had two parts. The experimental part was running shake table test. A lot of you may be really familiar with that because we have a great one here. And the uniqueness of my work was having a portable CPT on top of the shake table. So we were able to run the CPT test after each shaking event to just see the evolution of the strengths after the shaking events. And the other part of my study was running numerical simulations to study the seismic stability of the tailings dam. And I was basically modeling the tailings dam as with random fields and assigning random properties to the tailings instead of assigning uniform properties, which is far away from reality. So I'll stop here and move to what we do at Exponent shortly. So we have been involved with a lot of high-profile failures in the States and also internationally. A lot of you may recognize this picture. This is the bridge collapse in Baltimore that happened 1 year ago, and we are already working on behalf of one of the involved parties in this project. The top right one is the bridge collapse in Pittsburgh that happened like, I guess, 3 or 4 years ago. And we work on that case and help our clients to understand the causes and the failure of the mechanism of the failure. This bottom left one was a project that I worked actually last year in Los Angeles area. It's a huge landslide, and as you can see, it resulted in full destruction of a downstream construction area and significantly impacted 2 upstream buildings. And the bottom right one is the Orville Dam incident that I will briefly talk about it as part of my presentation today. And here is the agenda. We are going to start with the investigation process, which is the key process in any forensic engineering project. And then I'm going to present 3 of the projects that we have done at Exponent, and you can see how we approach the research-like questions in forensic engineering projects. And at the end, if we end up with some time, I'm going to talk more about Exponent and working at Exponent, and we wrap up the Q&A session. So let's start with the investigation process. So the purpose of investigation actually depends on who is your client. If it's a defendant or plaintiff, or it could be a government agency, judge, or public prosecutor. And depending on your client, your scope could be either of these bullet points or a combination of them, determining the causes or mechanism of the failure or the responsibility. And the main one is determining the causes, because once you know the answer to that question, it should be pretty straightforward to assign the responsibility to all the involved parties in the failure. So to determine the causes, you need to answer some essential questions about the trigger of the failure or origin of the failure, and also the underlying mechanism for the failure. And each failure has a primary cause besides some contributing factors, and you need to basically identify all of those. And to answer these questions, there are some input parameters that you need to know for your investigation and analysis, like the loads, resistance. If the failure happened during the construction, it should be the activities during the construction. If the failure happened after the construction, you need to know the as-built conditions or some environmental conditions. Maybe earthquake happened, or maybe there was a significant storm right before the failure. So, and at the end, you need to always establish the causal relationship. You need to show if there was a design error or some construction defects, or maybe there was lack of maintenance. But at the end, the goal is to show a causal relationship between the action or lack of an action and the failure. So let's define the trigger. Trigger is the event that caused the collapse occur at that particular moment. And it could be a variety of things, like added load. It could be environmental, like a significant storm, or construction, or storage, or usage. Or it could be earthquake, it could be a removal of a member that happens during renovation, or it could be undermining due to an adjacent excavation or deterioration of some members. So, but it's not really easy. And sometimes it could be really elusive to find that trigger. For example, the Champlain Tower that Exponent also investigated this failure, this tower was built in 1980 and had gone through several hurricanes, like the 1992 Hurricane Andrew. And even in 2018, there was a structural inspection and there was no note of imminent failure for this tower. But on a quiet night in 2021, it collapsed and it resulted in 98 fatalities. So, and the next question was the primary cause. And this is the important one, because without this event, the failure would not have happened. And sometimes it's different than the trigger. And that makes it really hard to basically identify the trigger besides the primary cause. And as I said, besides the primary cause, there could be some other contributing factors. And to identify them and see which ones actually contributed to the failure, you need to do some types of sensitivity analysis and isolation of the factors for your analysis. For example, you have 3 factors that could have contributed to the failure. So you're going to consider them, all of them first individually. And you may see that, for example, with factor A, you're going to be fine, in a safe zone. And in fact, with factor B, you're going to be in yielding zone. And factor C, you're going to be really close to failure. But at the same time, you can see that when you consider factor A and B happening at the same time, you're going to be in the failures. So with this introduction, every failure analysis could consist of a combination of these steps, or all of these steps. The first one is the field observation, which is really important. The next one is the document review. That could be reviewing the design documents or construction documents, or daily reports or operation records, or maybe there are some investigation from the past and you need to review those too. And after collecting all these data, if you still need some more information, you may need to do some additional testing, like lab testing or field testing. And the last one may not sound that fancy, like hand calculations, but it's always a really good first step to understand some probable causes of the failure. And at the end, if you are dealing with a complicated case and you need some flexibility with doing sensitivity analysis or exploring with some of the input parameters, we need to do some advanced analysis, like using finite element methods and some softwares that are able to do such analysis. So now knowing all these steps that may be needed in failure investigations, let's go through 3 projects that we have done. And for each of these, they vary in sizes and amount of effort that was needed to answer the question. The first one is a small project. It was about a foundation damage. It was basically an insurance claim, and we were working on behalf of the insurance because the insured was claiming that they had a recent crack in their foundation because of some leakage from the piping and probably some soil movement that could be expansion or collapse of the soil. But the main claim was that this crack had been formed recently. So the house was a single family wood framed house built in 1981 in Sacramento. So I did the site visit. First, the foundation system of this single family house was a perimeter footing with slab on grade in between. First, I noticed some cracking on the perimeter footing, and also inside the house, in this east bedroom, there was an east-west crack in the slab on grade. So, and then I moved inside the house and performed a relative elevations survey to basically see the pattern of the movement of the slab and the foundation. And here you can also see where I saw those cracks on the perimeter footing and the crack inside the east bedroom. And also there was a big crack on the ceiling. The first thing that you notice, there is this floor movement, the settlement of the slab on grade is not entirely consistent with the location of these cracks. So I made some more observations. The first one was behind this wall is the east bedroom and that big crack that was going through the slab on grade. The first thing you see, there is no distresses on the wall and also no crack on the tile. If this crack had been formed recently and it was that strong to make a crack in the slab on grade, it would definitely damage this wall or this tile. The next observation that I made are these wood tacks. They usually install these wood tacks to place the carpet on top of the slab on grade. I noticed no damage. They were not snapped out or anything like that. So if this damage was strong enough to crack the slab on grade, it could definitely damage this wood piece, but it had not done that. And the third one, which in my opinion was the most important one, was that the close look at the crack. You can see that the edge of this crack is kind of weathered. It's not showing that it has been formed recently. And more important than that, this crack is just nicely going around the particles. All of you have taken that laboratory course that you do testing with different type of material, and you do the compressive strength test with the concrete cylinders, and you see when you crack the cylinder, that crack goes through the cement part and particle part. It cracks everything. But this one is nicely going around the particles. So all of these observations made us to conclude that probably this was a placement error or a mixture error of the concrete. And it just formed shortly after the placement back in 1981. So, and we were able to answer the question to our client. And it was just field observations and some simple measurements. So now moving to the next one, it was about the lateral movement of the retaining wall during pile driving. And our client here was, this was a construction claim, and we were working on behalf of the contractor. So basically, they were developing this area with these 2 buildings. Along the south edge of this construction area, there was supposed to be a retaining wall. And during the construction, they noticed some unexpected horizontal movement of this retaining wall. And we were retained to evaluate the causes and some other contributing factors to the unexpected lateral movement of the retaining wall, which was a reinforced concrete with a footing that was sitting on top of some timber piles. So here, let's talk about first about these buildings. So we had 2 buildings, building A, building B, and some parking garage area. and this is the driveway on the south edge of this area, and this is our retaining wall. The foundation system for these building A and building B consisted about 1,500 timber piles that were about 65 feet long. And the foundation for the parking garage was precast concrete piles that were 65 to 90 feet long. And then here for the retaining wall, here is the drawing showing the details of the retaining wall. It was a reinforced concrete sitting on a footing, and the footing itself was sitting on 3 timber piles. One of them was vertical, and the other 2 were battered. And then on top of the footing, we had 2 cast-in-place piles to act as a foundation for the concrete driveway. And the whole purpose of this retaining wall was to hold this backfill. And the backfill was needed because they needed to raise the grade elevation for 10 to 11 feet to raise the grade elevation and make this driveway. And these 2 are timber piles. So I'm here to just give you a better visual. You can see the cast in place concrete piles that are sitting on top of this footing, and these 2 timber piles that you see here. And this photo was taken right before backfilling this area because they needed to backfill this area and then just place the pavement on top of that. So, and let's go through the construction sequence. So they made the cuts here to prepare it for placement of the timber piles. And then they place the timber piles. As you can see, the first row is vertical and these 2 are battered. One very important observation that they made during the construction was that when they placed these, especially the vertical timber piles, they would drop for 15 to 25 feet under their own weight. So it was showing them that they are dealing with very soft clay there. Moving forward, they placed that concrete footing, as you can see here, and then they cast in place concrete piles on top of the footing, and then they made a one-to-one slope to make a pad, a construction pad, just at the back of the heel of the footing here, and then they started backfilling here. And after that point, they started installing the timber piles below building B and parking garage that I showed in a few slides before. And around this time, they noticed some movement of the lateral movement of the retaining wall. So we were called, we went to the site, we noticed the widening of expansion joints, some diagonal cracks, some seepage at the bottom of the wall, and also some breaking noises while they were doing the site visit. So we installed some instruments to monitor any movement of the wall. We did some additional testing to better interpret what is going on in the subsurface and make sure if the assumptions for the soil strength was accurate or not. And then here are some of the results. You can see that, and they started from building B. They had not made it to building A, and that's why you don't see these dots. But these dots are basically representing the timber piles. So they were at this point when they noticed the lateral movement. And you can see the lateral movement was at the bottom of the wall was as large as 11 inches. And the outward rotation was about 1 degree. So we started our analysis. We compiled all the data, all our observations, and then we established the subsurface layers and their strengths. Basically, the first thing that we could think of was the global instability of the wall. So we use a slope W software, which is a limit equilibrium analysis you have heard of if you have taken soil mechanics or geotechnical engineering. So in this analysis, we consider the effect of this one-to-one slope, the reinforcing effect of the piles, and also you may ask why the color of the clay in these layers are different, even though they are next to each other. Because of the higher stir charge from the retaining wall, there are some reinforcing effect on these layers, and we even considered that. When we did the slope stability analysis, the factor of safety at the cross section with the largest lateral movement came out to be 1.5, showing that global instability is not the issue here. So the next step was doing deformation analysis, finite element analysis with a software called Plaxis. So the benefit of using such deformation analysis was to consider the effect of the construction sequence. As you can see, some excavation, some backfilling, and also the reinforcing effect of the piles, the soil and the structure interaction, and also the weight from the crane that was operating at top of the slope. So we first calibrated our model at a cross section that showed the least amount of lateral displacement. And after calibrating our model, we moved to the cross section with the largest lateral movement. But the amount of movement that we could calculate from this analysis was only 3.6 inches. But the observation was about 11 inches. So we still had not found the primary cause of this movement. So the next step was considering the cavity expansion. So we did the cavity expansion that basically goes over the undrained soil deformation around an area that you are doing the pile driving. So this is a very well-known basically phenomenon, but it's been mostly studied in stiff clays. In stiff clays, and this project is from Boston area. They did a lot of studies, a lot of measurements during this project, and they noticed that the influence zone in stiff clays from the pile driving could be 2 times the pile diameter. But here we had soft clays, so it could be less. So, and here are the formulas. I'm not going to go through the details of this formula, but basically you can calculate the lateral displacement due to the pile driving. And we need to calculate the critical radius beyond which there won't be any significant influence from the pile driving. And that critical radius is dependent on the shear modulus and undrained shear strength of your material. And you can see the stiffer it is, like the higher is the G, the higher is the critical radius. So after running this analysis and combining it with finite element analysis, the deformation analysis that we did, we noticed that at the section with the largest lateral displacement, combining them together, we could estimate up to around 10 inches of lateral displacement, which was pretty close to the observation in the field. So after doing all this analysis, we could make these conclusions. First, this was a foreseeable event. So the designer was the responsible person to just foresee this problem and figure it out and find a way to avoid such unexpected movements. And the primary cause was the pile driving and cavity expansion. But besides that, the building that one-to-one slope just behind the hill of the retaining wall and also the operation of the crane on that slope was the other contributing factors. So let's move to the next project. And I'm skipping a lot of details, so I'm gonna leave enough time at the end for questions. So the last one is the seepage behavior from fluctuating river levels. In this project, we were working on behalf of Department of Water Resources, UNR. So I need to give some background before going through the details of this project. So it was related, or it was a consequence of Orville Dam incident in 2017. So this dam is in North California, and it's the tallest dam in the States. It is 770 feet tall, and it has the main dam and the main spillway that you're looking here, and an emergency spillway next to this main spillway. So from the bottom to the top, it's 1 kilometer. It's pretty long. And when it's discharging water, it can fill out an Olympic-sized pool in 2 seconds. Yes, so it is equal to 300,000 cubic feet of water. So in 2017, around February, California was experiencing one of the wettest winters, and then they needed to discharge some water to bring the reservoir level below an emergency level. So shortly after they were discharging water from here, they noticed some weird pattern on the spillway. So they stopped discharging and they noticed this huge hole on the spillway and some erosion going on below here and also along the spillway. So then they started using the emergency spillway, which had not been used at all before this date. So it didn't work well, and it eroded this slope really fast, faster than what they thought. And at the same time, the weather was not their friend. The rain kept coming, so they had to discharge water from the main spillway. So they started doing that, and it took like 2 weeks. And around that time, they had issued evacuation order for 200,000 people downstream. And at the end, a lot of water was discharged to Feather River at the downstream. So here, the farmers at the downstream along the Feather River, they were claiming that this pattern of the water release and the amount of water that was released caused inundation of their farms and oversaturation that damaged their trees and also caused loss of product. So we were just studying that, and here again, this study was like a seepage analysis study. You can see that along the river, you will have the levee, and then as this river level goes up, you're gonna have some effects in the field on the other side of the levee. And there were some photos. These are from May. The incident happened in February. And this photo is around May, and they were showing some ponding water in their farms and showing that their trees were damaged. So to just give you some more background, it's not directly related to geotechnical engineering, but there are some similar basically concepts like in unsaturated soil mechanics. There's something called field capacity. Beyond the field capacity, your soil is going to get really close to saturation or oversaturation. And we all know if you don't water your plants enough, they die. But if you water them too much, they die. So the way the plant pathologists look at this problem is that, okay, we don't want to go over field capacity. And this field capacity is different for different types of soils. For example, as you can see, for different types of soil, the field capacity varies. For example, for clay, for silty clay type of soils, that field capacity, which is equivalent to the volumetric water content of the soil, is around 30%. So just keep that in mind. Later, I will get to this. So we needed to approach this problem and see if this incident indeed caused the problem that they were claiming or not. So we used the US Bureau of Reclamation, the design standard number 13 for embankment dams. And in this manual, they basically offer 3 methods to go over the seepage problem. The first one is graphical methods, just drawing those flow nets that you all have done in your undergrad courses. The second one is physical models, just doing like field testing. And the last one is numerical analysis. And that is the one that we adopted, because again, it gives us the flexibility to do some sensitivity analysis, to vary our input parameters and see how sensitive it is, the outcome to the input parameters. So we use the SIPW from, it's a module from GeoStudio software, and it uses finite element method to do the seepage analysis. And we needed to first collect all the input parameters for our study. So we did a lot of CPT testing and some boring logs next to our CPT testing to first verify what we see from the CPT, and also take some samples to run some laboratory tests to know the unit weight, the void ratio, the moisture content, and above all of these, the hydraulic conductivity of the different types of soil. And we did a lot of them. We did some that were just behind the levee, some of them that were far from the levee, because some of these farms were not adjacent to the levee. So we needed to do a lot of testing to establish that cross section just across the river. So here's just one example. You can see different types of soils, from silty sand to clay silt to clay and silty clay. They're all smashed together here. And from the geology, point of view, it was all alluvium and marine deposits. But again, from, for example, the hydraulic conductivity point of view, there were a lot of differences. And when we did the testing and we collected all the data, we could establish this 3D model of geology. And we needed some 2D models for doing the seepage analysis, but this level of complexity is not practical in practice. Nobody models the seepage analysis like this. So we needed to do some simplification. And also we had lower and upper bound for our permeability. So we needed to make some decisions. So after going over all data, this is a simplified geological cross-section that shows different types of material and also their permeability. And here, for example, this one you can see is based on 3 boring logs next to CPT testing. And of course, we had done some desktop studies, used some previous investigations and previous reports. So, and the other input that we need for the seepage analysis is basically the input from one side of the levee, and that varying river level that was basically an outcome of the release of water from the dam. So we had the hydrograph that was observed in 2017, but we needed something to compare that hydrograph to something that, what if this incident had not happened? So DWR had another consulting company to just give them a hydrograph representing a without incident hydrograph, but from the worst case scenario that was possible in this location. So we had 2 hydrographs, so we could do the seepage analysis for both scenarios and see if there is any significant difference between them. So let's look at GFX3 for the sake of the discussion. This is the model in CW. As I say, it's a finite element method. You have the river level here. And in the steady state, you can assume that the groundwater table is going to be like this. And here is the analysis that we did. The blue one is the hydrograph with the incident, which was observed in the field and it was recorded. And the red one is the without the hydrograph. And you are looking at the changes in the groundwater table below and beyond the levee over time. And you're going through the time. And you see that they are pretty close. And as we approach May, this groundwater table becomes really close to the surface and becomes like a ponding water. And that is important because after all, we need to make sure that our model is close to the truth and what happened. So moving forward, so around this time, this photo that I earlier showed was taken. And you can see that around this time, the groundwater table from our model was really close to the surface. So you may ask that probably we are still far from the reality, but the note here is that the model was not considering the precipitation, irrigation, evaporation, or these kind of things. And if you include those factors in the model, probably you'll get something like this. So based on these and a lot of other sensitivity analysis that we did, we believe that our model was accurate and we could make some conclusions. And also, we made some graphs and some conclusions at different points and at different distances from the river. And here I'm gonna just show the P1, which is the closest right behind the levee, and this number 4, which is farther from the levee, to just see how different would be the groundwater table after going through the differences in the hydrograph over time. So starting with P1, which is right behind the levee, you can see that there are some differences in the groundwater table. The solid one is with the incident, the dashed one is without the incident. And you can see that around this time in April, there are some differences, and that difference is still less than 1 foot. And here is showing the field capacity, the one that I was talking earlier, that volumetric water content, that if you go beyond that, you are basically overwatering your plant. And you can see that as the groundwater table goes up, even at the surface, you're exceeding that field capacity. And then let's look at a point farther away from the levee. You can see that almost there is no difference in the groundwater table, and the field capacity had been exceeded over time, even at the surface. So based on these, we could make conclusions. First, the differences in the groundwater table due to the fluctuating river levels was most pronounced at the area close to the levee. And as we were getting farther from the levee, that difference was diminishing. And then the last one, we can see that the groundwater table and field capacity was very similar for the with incident and without incident cases. And the last one was that the with incident and without incident scenarios produce essentially identical responses at the subject location. So in a worst case scenario that was expected in significant rain, you would have the same problem in the absence of the problems with Orville Dam. So the Orville Dam, the incidence and that irregular release of water was not contributing to the issue in the farms in the downstream. So that was the end of the three projects that I wanted to, again, briefly talk about. And I just want to briefly talk about who we are in just 3 slides, and then we're going to jump into Q&A session. So we have more than 900 people, and we have offices across the states and also offices in Europe and Asia, and we were established in 1967 by 3 professors from Stanford, and since then, the main work that we do are forensic engineering. We do some proactive projects, but the main part of our works are reactive projects. And we have 90 plus technical disciplines. Today, my office is Oakland, my affiliation says Oakland, but we have offices all across the states. And here you can see that more than 70% of our employees have PhD and they have expertise in their own field. And here are all the disciplines that we have. Here I'm representing civil and structural engineering practice, which is under the infrastructure and materials discipline. But we have worked on many multidisciplinary projects. Myself, I have experience working with people from mechanical and thermal and even polymers and biomedical. And it's been a great experience to just learn from people that have very different background and learning from their soft skills and also some technical skills that you never had the opportunity to learn about those things. And I just cut this short. If you are more interested, I would be happy to chat about it more. I encourage you to introduce yourself to us so we can continue this discussion. And in the future, if you would like to consider exponent for your career, we would be really happy to have you. And now I would welcome any questions about all the topics that we talked today.
Thank you so much. Thank you. Thank you. Thank you so much for the presentation. And yeah, any questions? So someone immediately.
Have you faced any ethical challenges?
Oh, press the button again. No.
Talk loud. Yeah. Have you faced any ethical challenges regards to like giving a decision in favor of your client or like having this decision like which has like anything that favors your client? Have you faced such?
Yeah.
Can you share some?
Sure. Yeah, that's an excellent question and a question that is always asked. This is always the first question that people ask. No, it's not like that. They may say that we may say stuff in favor of our clients, but that never happens because we are a scientific consulting company and we do everything scientifically, and whatever we say is evidence-based. And in a lot of projects, we do them in phases, for example. We tell our clients that, okay, we can do some document review and we will let you know if you have any chance or not. If everything is against you and you have made a mistake, you just tell them, okay, we cannot work on you. And, I specifically don't or haven't said that we represent our client because we do not represent our client. We just work on behalf of our client. And we only work on behalf of them when we see any merit doing that. And we don't tweak data or anything that is not true to just help our client. We don't do that. Yeah, I don't know how much I could answer your question. Yeah. Yeah.
Okay, excellent presentation. Thank you. So my question is, as a part of your diagnosis of the reasons, working with clients, have you worked closely with attorneys or have you testified in a court? When these issues go to court and litigation.
Yeah, that's a great question. Yes, our clients mainly are either insurance company or government or lawyers who are working for these people. I would say 50% of my projects, I closely work with lawyers, and always we need to make sure when we write reports or we make a presentation for them, we make them in plain language. So they need to understand our reasoning because they will need to use these reasonings in the court. Or if we are giving something to a judge, again, we need to speak somehow their language. And we write the report and we give them to the lawyers, they review that, and then they give comments to us. Again, not telling us, don't say that. It's not like that. They just say, okay, this might be irrelevant or it might not be clear for the audience that we have here. And yes, we do work with them and somehow we become like them, like, not talking, we just answer the question, just not throwing irrelevant information because always in the positions, it becomes like a mind game because lawyers are not as technical as you and they want to somehow make you say something that is not correct. So it's like a mind game. I've never done a deposition, but I have read a lot of transcripts, and sometimes they just come to crush your confidence just in the beginning. It's something really irrelevant to the case, but yeah, and that's another fun thing about working on forensic engineering because that part is very irrelevant to engineering. You're developing a different set of skills. Yeah. And another thing that I want to add before going to the next question, the business model of our company is seller doer. I don't know if you have heard that term, but as you go up, you need to build your own network, have your own client and bring project. It's not like contractor company or design company that there is a big project that goes for 4 years and you're working on that project for 4 years. I have worked on some projects that their budget was 10K. I had to just give the report in 2 weeks. And I have worked on some projects that were like $1 million. They had budget for $1 million. But at the end, for going up in the company, you need to bring your own client. And it's a little bit similar to what faculty do. They have to, at the end, define their own niche and the research that they do. They have to submit proposals or reach out to different people to bring money. Yeah.
I saw one in the back of the banner. Great presentation.
Yep. Oh, okay, great presentation, thanks. My question is more related to, from a percentage basis, how often is it the design that is the problem versus construction techniques? And then also I would ask, how often is the result indeterminate?
Yeah, I have to answer that question from my experience. So don't quote me on that, but for my projects, believe it or not, the majority was construction defects. In one project that I had, the retaining wall that was supporting a water tank was moving. And after reviewing the documents, we noticed that the design was for a 10 feet diameter tank, but when we showed up at the site, the tank was 35 diameter. So the surcharge was much higher. So and nobody knew because we were working on behalf of the owner, and the owner had bought the property right after the construction. So they didn't have a lot of documents. So they didn't know at what point the size of the tank had been changed and who approved it and why they didn't change the design. So, and about your second question, so far I haven't had an experience at the end saying that we don't know what caused it. We have had some projects that the opposite party said, for example, this is because of the leakage. And we go and study, compile the data, and we prove that, okay, the seepage or the leakage here could not have caused the failure. It could be something else. But our work ends there because we just need to show, so in some of our projects, we just need to, for example, say, this claim is not true because of these evidences and these analysis, but we don't know what is causing it.
Yeah.
Thank you so much for the presentation. My question is about the second topic with the pile-driven foundation shifting. So you said at the end, basically, it was a design and construction error, right? It was a combination of the two because of the crane. So at that point, like, what happens? Are both parties at fault, and how did that end up working out?
So it was mainly design issue because they had to have the crane at the end. But for example, they could make it a certain schedule for installation of the timber piles instead of installing all of them back to back and increase that pour water pressure that initialize that on-drain movement. They could say, okay, you only can install 3 piles and then give it some time, go install somewhere else, something like that. Or they could limit the weight of the crane because at the end, you need to have some equipment. So mainly it was a design issue and nobody warned the contractor that something like this would happen. Otherwise, they could come up with a solution or they could talk to the designer and say, okay, let's figure out a solution before having that problem. Yeah.
Thank you. Yes, very nice presentation. I have 2 questions. One is kind of generic, the second is a little bit more specific. So you mentioned at some point of your presentation that some of these problems are foreseeable, right? So I wonder whether you meant that within, the scope of the project, like with the information they had, or whether they should have identified and raised a red flag, say, hey, we need to investigate this more. Because sometimes perhaps the budget available during the, let's say, site investigations phase or the analysis phase can be also constrained, right? So I wonder if, of course, perhaps we can find out earlier, but is that a realistic, was that a realistic situation, right? Where we have the budget to investigate and learn what could have been a problem? The second question is on slide 55, you show a cross section. And you said that you ran some sensitivity analysis to do the seepage analysis.
Okay.
And your results were very accurate. So I wonder what type of sensitivity analysis you did, if it involved permeability, cross-section, variation, because you have also some like 3 investigations and some stratigraphy. So if you can comment on that, it would be great.
Yeah.
Thank
you. Thanks for the questions. For the first question, let's see if I can go back. You said 55, right?
Yeah.
Yeah, about the first question, sometimes may not be practical. You may need to do a lot of testing to know everything. But in that specific case, for the lateral movement, you need to know about cavity expansion, And again, we went over a lot of details, but even they had made some mistakes in interpretation of the soil strengths. We noticed that the soil strengths that they had assumed was 50% more than what it should be. And I mentioned that the timber piles were dropping 15 to 25 feet when they were installing. So now at that point, they could say, okay, let's pause and reevaluate our design, but they didn't do that. But I agree, sometimes it's not practical. We get a lot of projects, a lot of design build projects, like interested specifically on the East Coast. They have like 10 borings, 20 borings, and based on those borings, the contractors go out and bid on the project and say, okay, we make this project with 20 millions. It's like interesting. But once they start a project, they thought that there is like 10 feet of clay and they can go over the consolidation with some surcharge in 2 months. But as we penetrate the soil more, they do more testing, they notice that, oh, in some places the clay is 30 feet and we are going to be behind the schedule, and they claim differing site condition. So that's not fair, because you needed to do more desk study or some more testing. So in this specific case, I believe that it was foreseeable and they could at least think about the presence of the soft clay, and also the cavity expansion. It was pretty well known in clays. Yeah. And the second question about, and you can follow up with my answer if it was not satisfying, but about this one, the main thing that we were changing was the hydraulic conductivity. We had a range for our hydraulic conductivity. So we were changing that. And even after that, we noticed that for our question, it was their effect was pretty insignificant.
Thank you for the answers. I just want to follow up on this one. So that what informed the selection of this poorly graded sand, I think is at the bottom on the left, and in between the two, I think these are CPTs or two investigations.
Yeah.
Yeah. So what informed the selection of that cross section?
For this one?
Yeah.
Yeah, as I said, besides this, we had done a lot of desk studies. So, for example, I don't know if you're familiar with there is a website, it's for the agricultural department. It's the US soil web soil survey. So when you go on that, it gives you a lot of information about the depths of the soil. There is another resource, it's called GeoTracker. It's about a collection of, for example, leakage from gas stations. On that website, all across the specific California, I'm not sure about Nevada, but you have a lot of historic borings that you can't just land. Yeah, besides these ones, we had done a lot of this study. Yeah.
Right.
Yeah.
Hamid, go ahead. Thank you for your presentation. It was really interesting. And I have a question for your last project, the dam project. You noticed that after they released the water, there was a big hole or damage in the dam structure. Could you study the reason of that one? I mean, can we relate that to the cavitation or something like that?
Sure. Thanks for the question. I believe you meant the damage or the hole on the spillway, not the dam, because dam remained intact, fortunately. It was not our scope to study that and come up with the cause of that problem, but now there are many studies and the reports are out. But to just give you a summary why that was caused, they found out there were a lot of cracks on that spillway, and when the water goes down, it can seep through those cracks. And based on like Bernoulli, when you're going down with that velocity and then you go through a crack, when you go below the slab, that velocity turns into head. So it can push the main spillway up basically. So it crushed the slab and then started eroding the soil below that. And they found out that there was a lot of inadequacy in the geotechnical investigation back when they were constructing the dam. They thought that the soil, basically that spillway is sitting on a bedrock, but they noticed that the bedrock was pretty weathered and the soil was pretty erodible. So there were a lot of inadequacy in the initial design and also the maintenance.
All right, let's do two more. We'll do one in the back and then Alejandro.
Thank you very much for coming and presenting to us today. When I was a student, it was hard to meet people as approachable as you, but also as accomplished and working at such a high level. So thinking about your own career progression to this point, would there be things that you would recommend the students do in terms of opportunities on campus or classes? Or if you think back on your own experience, opportunities you wish you had taken at this stage or classes or so on, that would have helped you in your career?
Yeah, this is a really great question. Again, I talk from my own experience. You know, technical wise, I know your university is really good. Faculty are great. I know a few of them. I'm sure that you have access to a lot of technical knowledge and you won't have any issue with that. Some other things that are really important for your career in the future, maybe at some point I struggled with that too, was soft skills. Like last week, I attended a conference, Geofrontiers, and I noticed PhD students doing a lot of great works, but they were not able to coherently present their work. And that was really sad. And besides that, when you look at the writing, they cannot coherently start from what is the problem, what was the means and methods, how they approached it, and what was the conclusion, and what were the evidences or analysis. So courses, if there are no writing courses, again, I'm not talking about just the grammar, because I was TA for example, lab course. I was the international students and there were a bunch of native speaking and it was horrible. You know, it's the writing is a different skill. And yeah, taking courses like that or like some speaking skills or how to present something, that would be really, really critical for a career in the future.
All right, Alejandro with our last question.
Okay, thank you. Thank you very much for your presentation. I'm a little bit very curious about the project where the random field theory was used. Was there any specific topic being investigated? And did this help to make any better informed conclusion?
Okay, yeah, you're now talking about my PhD, which was 5 years ago. So for that one, I was using the KL expansion method to just form that random field. And I don't know if you're familiar with that method, but there are some other methods like the Gaussian processing that you can use those. But I use that method specifically. And as you may know, you can have infinite number of random fields. So I was using the hyperbolic sampling to just come up with, I think I used 66 realizations for the tailing. So I did 66 simulations for specific shaking event or seismic event because I was considering different events too. And I was looking at the co-seismic of the dams for different shaking events and also different realizations. And one conclusion that we're making, there were for the same, for example, average value for your undrained shear strengths of the tailings, there were some cases that stayed safe with limited movement, but there were some cases with very large movements or even failure during the post-seismic period of the shake. So yeah, but you can review my publications. Right now, I don't remember the details. I need to take a little bit more time, but yeah, you can contact me if you're interested. We can talk about the details more.
Thank you very much.
Thank you.
All right, with that, we'll wrap up questions and then let everybody go to pizza, which by the way, our speaker generously provided. So make sure you give them a thank you. But with that, thank you so much.